Hey Shaler area, welcome back. This is the Unit 2 note video number 5. In this video we're going to wrap up part 1 of Unit 2. We are going to talk about the behaviors of gases, which means since we just talked about all the different phases of matter and what you call it when you move from one to the other, we're going to focus just on gases today in this note video and talk about what happens to gases when you tinker with the pressure and the temperature and the volume. Since remember, gases don't have a definite shape or a definite volume, those things can kind of all be played around with. After this note video is over, we'll have a booby trap, and then you'll have your quiz on part 1 of Unit 2, chemistry, your first quiz in chemistry. So, since gases lack a definite shape or volume, to really understand what they're doing, we need to take a closer look at the things like volume, temperature, and pressure. So let's step back, or step forward, and see what all the little particles are doing in a gas. In your bedroom, classroom, house, whatever, wherever it is that you're listening to this note video, the room temperature is probably about 20 degrees Celsius. Remember, that's one of the temperatures that you have to remember in Celsius. So that's room temperature. That's a typical, normal, comfortable temperature to be sitting in. The average speed of particles of air, remember, air is a homogeneous mixture of a whole bunch of different gases. There's oxygen gas, nitrogen gas, carbon dioxide, there's water vapor up there, there's a whole bunch of molecules floating around in the substance we call air. But the average speed of the particles in the air is 500 meters per second. That's really fast. Now, that doesn't mean one molecule is going to be like flying all the way across the room, because they can't quite do that because there's a whole bunch of stuff in the way. There's a lot of other molecules. So but they can move a relatively short distance before they slam into something and cause that object to go careening off, and while they go careening off into another direction and bouncing around. So they're all this constant, it's like a ball pit where all the balls are just bouncing all over the place and moving fairly violently. It's just that they're so small that we don't see or feel any of it going on. This is a really fast speed. It's twice as fast as a jet airplane. So these little things are moving super fast. And every time one of these molecules of air bounces off of your skin, hits you with this really high velocity and bounces off your skin, we call that air pressure. So air pressure is essentially the number of times, it's the rate at which these things are bouncing off of you. So like the number of times, number of collisions per second with the air molecules with your skin. The more of those that there are, the higher the air pressure, the fewer of those collisions that occur, the lower the air pressure. And we've talked about lots of times about what happens under great pressure and under small amounts of pressure. We don't need to go into that now. But that's where air pressure comes from. It's the slamming into you of all of those little air molecules as they move around at really fast speeds. So pressure, since we brought it up, we should define it, is the force of a push that is divided over the surface area of an object. So if you were wondering why we had to calculate surface area before, one of the reasons you have to learn to calculate surface area is so you can calculate pressure. So the formula for pressure is P, or pressure, equals force divided by surface area. And the unit that we use for pressure is pascals, as we saw in the chart the other day. And this is named after Blaise Pascal. I love his first name. His first name's awesome. Blaise Pascal. He did a lot of things in science. He invented one of the first calculators. He studied a lot of stuff with fluid dynamics and hydraulics. He just did a whole lot from a young age with science. He's a pretty well-known name. You got to be pretty well-known in order to have somebody name a unit after you. So there are 3 laws. There are 3 laws of gases and their behaviors. And you're going to need to know all 3 and know specifically what each of the 3 is talking about. And they're all fairly similar, so you're going to have to spend a little bit of time sorting these out in your head. So the first is called Boyles Law. And while they're all pretty similar, they're all also really simple, which can make it so that you easily confuse them. Boyles Law says, Boyle is based on the work of Robert Boyle. And Robert Boyle had a lab assistant that became really famous. He doesn't have a law named after him, but he might be even more famous than Boyle. And Boyle's lab assistant's name was Robert Hooke. Hopefully this is a name that sounds familiar to you from your 7th grade years, and actually more like your 3rd and 4th grade years as well. You probably learned about him. He is a pretty important human being to know his name about. Maybe you'll remember. Anyway, Robert Boyle did a whole bunch of work with gases and pressure, and to boil his work down to one sentence, essentially, when you increase the pressure of a gas, its volume goes down. These gas laws are not like revealing, they're not mind-blowing. It's kind of like common sense, but if it wasn't for these people, this is who we've named this pattern of observations after. So Boyle's law says when you increase the pressure of a gas, its volume goes down. You can see this probably most easily with something like if you had a syringe without a needle on the end, so like a tube with a plunger, and you plugged the end and you pushed on the plunger, you would be increasing the pressure on the gas on the inside, and its volume, you could see, would be getting smaller and smaller and smaller and smaller and smaller. The more pressure you put on the gas, its volume gets smaller. So it's kind of a no-brainer. One of the ways that I remembered Boyle's Law when I was a kid, there used to be a comic strip called Prince Valiant, and I always thought that Boyle looked like Prince Valiant. And the initials for Prince Valiant are P and V, and pressure is the P, and volume is the V. But it's not a comic strip that anybody reads anymore, so it might not be the best thing for you. Kids in the past have said that his picture makes it look like he's wearing this ascot that he's wearing. They say is his vomit protector. And again, V is for volume, and P is for pressure. So however way you want to remember that Boyle did pressure and volume, that's up to you, but something to keep straight. The next gas law is Charles's law. Charles's law is named after Jacques Charles. He was a person who did a lot of hot air ballooning when hot air ballooning was just becoming very, very new. So he was a pioneer at hot air ballooning. So a lot of things with air were really important to him. And his pattern of observations that are named after him say that when you increase the temperature of a gas, its volume goes up. I mean, you can see that very clearly in a hot air balloon. If you've ever seen a hot air balloon work, they use those flames to heat up the air inside the balloon, and it makes the balloon blow up. So when you heat up a gas, the volume gets bigger. It's because of Charles's law that you don't want to throw something like a sealed container onto a campfire. If it's sealed, the gases inside it will get hotter and hotter and hotter, and increase in volume on the inside of that container until pressure builds up and the container blows. So, according to Charles's law, when the temperature increases, the volume will also increase. There was a TV show that I used to watch when I was a kid called Charles in Charge, and I used to say that Charles in Charge was must-see TV. Sometimes they say that on commercials. So the temperature is the T, the volume is the V. So however you want to remember thinking of Charles's law, remember that Charles's law is about temperature and volume. Maybe if you wanted to remember that he was the hot air ballooner, you could think that when you increase the temperature in his balloon, it can take him out to the vacuum of space. So there's another T and V to remember. And the last law is Gay-Lussac's law. So this is the third gas law, and it's named after Joseph Gay-Lussac. And his law says that when you increase the temperature of an object, when you increase the temperature of a gas, these are gas laws, that the pressure also increases. So I guess throwing a sealed container onto a campfire would probably be more about Gay-Lussac's law than it would be about Charles's law. The best way to remember Gay-Lussac's law is to take note that his name has a hyphen in it, and you can think of a hyphen as a punctuation point, and there is your temperature and your pressure letters. So the hyphen in Gay-Lussac's name is a kind of like a point. It's a punctuation point, and it uses pressure and temperature. So you should take a moment to review those three laws, and kind of do something to keep them straight, and make little notes on your notes about how you're going to do that. So the quick checks come next. These should be super simple for you. Here are graphs that illustrate each of the three gas laws. You just have to identify which graph goes with which person's law. And this is what quiz questions will look like. There will be a couple of quiz questions like this where you'll have a graph and you have to say which law it belongs to. And that's why it's really important to remember the two variables, because the two variables are going to tell you which law it is. And then if you look at the graph, it illustrates what's happening with the law as well. But the easiest way for me to remember them is to just memorize which variables go with which law. So zoom through these because they're in your notes. We'll talk about them in class. All right, the last two parts of this section are the two application parts, where we're going to take everything that we've learned and kind of tie it together into something that's actually useful. So let's apply all of these loose connection concepts that we have into something that you find useful. So a heat engine is the name given to anything that turns heat energy into mechanical energy. So you know what heat energy is. Mechanical energy is the energy of motion. So kinetic energy is an example of mechanical energy. So there's two kinds of heat engines. There's the external combustion engine. And this is when the actual burning or the actual heat origin is found outside the piston of the engine. So this is a really good example of this is a steam engine. External combustion engines aren't used a whole lot anymore. But it's where engines got started. So in a steam engine, you have a fire, so they would burn coal to keep it really hot, but you could also burn wood or whatever it is you wanted to burn in this external burning chamber. And then a big tub of water that would then get really hot from the fire and turn into steam. The steam would go through a series of pipes, and then they would push a piston, and then the pressure would be released, and push a piston, and pressure would be released, and push a piston, and pressure would be released. That's how an external combustion engine works. But you are far more familiar with internal combustion engines. And this is when the burning actually happens inside the piston, which is inside the motor. So if you've never actually looked at a motor or seen how a motor works, it kind of just seems like magic. You turn the key and it makes the car go. But what's happening inside that motor is there's a lot of stuff going on. But at its core, this is how the motor works. This is called the piston, and there's different kinds of motors. This is how what's called a four-stroke cycle works. And essentially that just means that there's 4 positions of the piston while it's doing something. So in the first position, you have, so in case you don't know, a piston is a sealed cylinder. So there's a cylinder here that's going to have some explosions going on inside of it, and it's got a couple of little doorways that come out. You have one little doorway that can open up and gas can come in and air can come in. You have another little doorway where things can leave, and this goes to your exhaust pipe. This comes from your carburetor. I guess most cars don't have carburetors anymore, but this comes from your air intake and your fuel system. And then also plugged in here is the spark plug, which hopefully you are at least familiar with that cars have spark plugs. So all of this stuff goes on in here. This gets pushed back and forth because of what happens. And down here you have your crankshaft. So this you can think of as kind of being like connected to your tires. So when this goes around, it turns some stuff on your car like the drive shaft, and the drive shaft goes to your tires and makes the tires turn. So this part spinning makes the tires turn. So what's going on in here? Well, you typically have a number of these in your car. So if you have a 4-cylinder engine, you have 4 of these that are all doing something slightly different. It works in a sequence. A V6 has 6 of them, a V8 has 8 of them. So the more of these that you have in your motor, the more power your motor has. Also, the more gas you end up using. So this chamber opens up, the little door opens up, the air and the fuel gets like kind of spewed into here. There's a little sprayer that kind of like sprays the fuel so that it kind of evaporates immediately. It mixes it in with some oxygen-rich air, and then that door closes. So now we have a sealed chamber with explosive fuel in it. Well, that's not quite enough for the motor right now. People who design these motors want even more than a sealed room of combustive gas. So the piston then spins, and it actually pushes up, and it compresses this gas. So now not only do you have a little tiny room filled with a explosive gas, but now we are going to compress that so that it's under a lot more pressure. Now all the atoms are really close to each other. It's even more explosive when you do this. The temperature has gone up, the reaction is going to happen faster, and then the little spark fires. So both of the doors are closed, so nothing can get out, nothing can get in. The spark fires, we have just the right amount of oxygen and explosive gas in here, and what's going to happen? Well, it goes boom, it gets really hot, the pressure increases, the volume wants to increase, and that blows this piston back down, causing the crankshaft to go around. And when it blows it back down, it spins around, and when it pushes back up, when it comes back around again, the exhaust little door opens, and it pushes out all the smoke and spent fuel that just blew up inside of there. And then after that, that door closes, this door opens, and on its way back down, it kind of fills back up, and it shoots in more gas. And that just happens a lot. That keeps going and going and going and going. The gauge on your car, called the RPM, is what is measuring how fast this is going around. That's rotations per minute. And it's usually measured in the thousands, like 2,000. I think my car idles at like 1,800 RPM. So this thing is going around 1,800 times in a minute. So it's no joke. There's a lot of stuff happening pretty fast in that motor. And if any of that timing gets messed up, so like if the spark doesn't fire at the right time, or if something happens with the timing of the opening and closing of the doors, that makes the engine not work as well. If this door was open, for example, when the spark fired, it wouldn't blow the piston down. It would actually kind of blow most of the pressure out the exhaust pipe. You can have all kinds of things happen in your car. If your motor's not working right, sometimes it's because this system is just not working with the right timing anymore. That's how a motor works. Well, how does something get cold? So all of you have a fridge in your house. So we're going to talk a little bit how a fridge works. Now, I don't expect you to be a refrigerator repairman or have super detailed knowledge about this, but you should be able to explain when we're done here what's kind of happening at each of these different steps inside the refrigerator cooling system, and how the gas laws and how the states of matter are causing this to work. So what a fridge does is a refrigerator takes the heat from the food that you put in there, and it takes that heat and it pumps it out into the air of the room. So in order for a refrigerator to work, it has to be, the inside of the refrigerator has to be separated from the air of the room. So if you leave your refrigerator door open, your refrigerator won't keep the food cold. This is also how like the air conditioning in your house works and things like that too. We can make connections to that, which is why if you leave the doors of your house open, your air conditioning won't work. So anyway, let's start inside. So I take whatever, I just had some food for dinner, some maybe a piece of steak, we'll say, and a potato, and I don't eat it all, and I take it and I put it inside my fridge. So now it's inside my fridge. There's some warmth to it. Maybe it's room temperature because it's been sitting on my plate for a while. Maybe it's still warm from being cooked, but there's some amount of warmth to the food. Well, that warmth kind of moves into the air. The heat moves from the food into the cooler air, because remember, heat always moves from where things are warmer to where things are cooler. And then this stuff kicks in. So you have all these pipes that kind of run through the walls of your freezer and in the different spots inside your fridge. You have to be a little bit careful whenever you're kind of monkeying around. Mr. Reagle once, when he was in college, was trying to the ice in the freezer in my apartment had built up so thick that you could barely put a hot pocket in there. There was literally like 4 inches of ice along each sides of the freezer, and I was trying to chisel it out with a screwdriver once, and I actually punctured through the bottom and punctured one of these pipes. It was not fun. So be careful. Don't ever use a metal implement to scrape ice out of a freezer. Anyway, so the heat from your food ends up warming up the air just a little bit, but the stuff in this pipe is a special kind of fluid called Freon. And Freon doesn't take a whole lot of heat to evaporate. So in the pipes, when they're in your fridge, it's a liquid. But you put the slightest amount of heat up to it, and that liquid will evaporate into a gas. So the room temperature steak that you're putting into your refrigerator has enough heat in it to take the liquid Freon in the pipes of your fridge and evaporate it. So it doesn't take very much energy at all. So now we have an evaporated gas in this pipe, and it's now going to start moving out of the fridge. So it has absorbed the heat from the food. But it's still chilly. It's still cold. It's not really that warm because all it was doing was absorbing heat from a room temperature steak, for example. Well, that gas now goes down here to the most important part of your fridge. If this breaks on a refrigerator or a freezer, nothing will work. And typically when your refrigerator breaks, it's because this thing starts to fail. This is why refrigerators go bad, is this unit right here. This is called a compressor. So all it does is take the gas that's coming out of that pipe and applies a lot of pressure to it. So it squeezes it down. It's kind of like a little pump, and it's kind of, forcing lots of pressure onto it. Well, that causes it to get hot because of the gas laws. You add pressure, it makes the temperature go up. So now we have a gas that had the heat in it from the food, and now we've made it really warm. And now that we've made it really warm with high pressure, we send it into a whole series of really tiny pipes that are behind your fridge. Sometimes you'll also have a fan that's back there that's constantly blowing air over these things. Well, because of the way heat moves, you have a really high temperature gas that's under lots of pressure, and it's warmer than the air in your room. So if you ever put your hand behind the fridge when it's running, it'll feel like warm air coming off of there. So since it's warmer than the air in your room, well, what direction is the heat going to move? The heat is going to move from where it's warmer to where it's cooler. So the warmth of the pressurized gas here is going to move into the air of the room and make the air of the room behind the fridge warmer. Well, that gas now gets up here to something called an expansion valve. Got a little ahead of myself. There's a line that says what's going on behind the fridge. That gas that's now lost heat to the room goes into this little spot here called an expansion valve. And that I should say it turns back into a liquid because it's lost some of the heat. So as it loses the heat to the room and it goes through this expansion valve, the pressure greatly reduces. So in the expansion valve, it's going from tiny little pipes to now thicker pipes. So the pressure goes down a lot, and when the pressure goes down, the temperature goes down. And now you have super cold fluid that's able to go back into the fridge and suck up any more heat of any food that's still in there. And this is constantly cycling. It's constantly going and cycling through. And every time that so like every second that it's happening, it's pulling more and more and more heat out of the food that you've put in your fridge until everything in your fridge is really cold. Well, if you think about the repercussions of this, if your house is really hot, like let's say that the superheated gas that's back here is 95 degrees as when it comes out of the compressor, and your house is really hot, like your house for some reason is 95 degrees, like it's a really hot summer day, your refrigerator actually won't work. Because in order for your refrigerator to work, the pressurized gas that's going through here, it has to be warmer than the air that it's going through, or else it's not going to lose any heat, and it's just going to keep staying kind of like the same pressure as it goes through. My parents built a house down in South Carolina and moved down there after they retired, and I went down to visit them, and they have air conditioning because it's really hot down there, but there's no air conditioning in the garage. And my dad had a refrigerator, like a little mini fridge out in the garage, and he was complaining about how the stuff that he had in there was never getting cold. And I was like, it's because your garage is like 150 degrees. So the refrigerator actually can't work if the air is so hot. So he hooked up some fans so that he had constantly had fans blowing across the back of the fridge, and that actually was enough to help with the heat exchange, and his refrigerator started working. But that compressor was running like crazy, and it just could not get the stuff hotter than the air in the room, so the refrigerator couldn't work. So on your air conditioner, if you have an air conditioner, if it's like a house air conditioning unit, this part with the compressor and these coils is the unit that's outside. It kicks on and the fan blows and you can feel kind of like the warmth coming out of it. That's the warmth from inside your house that's getting pumped outside. If you have a window unit, the part that hangs out the window has that stuff on it. And that wraps up part 1 of Unit 2 of Chemistry. So we have talked about lots of things with temperature and thermal energy. There was specific heat stuff that we discussed. We did the phases of matter, what you call it when it goes between them, and the gas laws. So we've discussed a lot about molecular mechanics of matter. So what is going on with the molecules that make up matter? And that is going to be the focus on your first quiz. So good luck.